7 to 9 p.m. This is not a like this live interaction is teaching because session is planned in such a way that handle the interaction component between the teaching assistants, which is me and who wrote earlier, and the students of the school, so that if you have any doubts, any questions which you want to ask, so you guys can put both the questions and simply ask your doubts, get your doubts cleared, discuss it. Also, this whole session is being recorded, so after recording, we'll upload this session on YouTube. Link will be shared with you guys. So don't worry if you miss this live interactive session, you can go through the video. But I will suggest we participate in the live interactive session. That will also make you guys to think critically about some questions which we will discuss. Don't worry about anything. If you want to ask something, please feel free to ask. We can have a good discussion, then we can arrive at the result. So, live interaction session have planned in a way that if you want to have a summary of the lecture, so I will first discuss some important topics, summarize the lectures, and then we'll solve the quiz question assignment questions. So these assignment questions are not from current run of this course, these are from previous run of this course. So those assignment questions will be discussed here. So that will help you also to gain a good grasp of understanding that how these questions has to be approached and how you can score well in the assignments. Okay. Apart from that, sir, please question 10 in assignment. Go to Venkata. Actually, we can't discuss the current assignment. Okay, so we have been forbidden by the NPTEL to discuss the current assignments. We can only discuss the questions from the past assignment. So don't worry, when we will discuss those questions, you will get the good understanding that how these assignment questions can be, how it can be solved, how the approach should be. Okay. Don't worry, I will solve all these questions in detail. But I want you guys to actually try solving these in the live interaction session and see that how it can be solved and where you are making mistakes and how those mistakes can be corrected. Okay. Don't worry about this. Venkata, you will see this. I know the 10th question number 10 you are asking that we lost percent and everything. That is a very good question, but if you have gone through the slides, you will be easily able to solve that question. So I will tell you to solve that. Okay. So I think there are five, 7 people are there in the meeting. So if let's say let's wait for 1 or 2 minutes for others to arrive so that we can start the session. So before that, let me have some slides. So first, I will introduce myself since this is our first interaction session. So I know you guys are actually here to see what happens in the live interaction session. Maybe you have attended some other video before, so you must have a good idea about what interaction sessions are. So don't worry, have a interaction session. So I will start with myself. I will give a brief description of this course, and then I will call you guys also like what are your experiences in this course. I share slides. Okay, so once again I welcome you all to this live interaction session of this sustainable college discuss more about renewable systems. The system, but apart from renewable, there are other systems also. System. So we need to know what is a sustainable system. So what is the meaning of what system? So once again, welcome all to this live session one of this course. So this course is being taught by Professor Pankaj Kalita. He is Associate Professor in IIT. I am Mohit. I am Prime Minister Research Fellow in IIT. So I will be taking this live interaction session with you. Okay. So don't worry, we'll have a good interaction. I'm sure. So this is about me. I'm a doctoral student at Environmental Science and Engineering Department of the Institute of Technology. I'm also a practitioner research. So as a part of our fellowship, we need to interact with the students of courses so that we can have a good discussion and can also listen to your queries and solve those queries, okay, or have a good interaction, or can give whatever we have learned through our doctoral studies to you guys, so that you guys can develop a good understanding about some different topics and various topics. Okay, so this is what it means. So live session teaching methodology will be same. We will meet every Tuesday at 7 9 p.m. Don't worry, this is not a lecture course, so you will not be get bored with lectures. I don't want to bombard you guys with the lecture series and everything. We'll have a discussion, simple. So come with questions, we'll discuss. You can discuss anything, even if you don't have question, you have listened something, you have read something, come with them. We'll have a good discussion on that. Okay, and this is what this course is for. Discussion on the topics taught in weekly lectures, doubt clearing, interaction with the students, any questions related to live session that can be raised. Questions will either be addressed in the forum or in the live session. Okay, so this is how we will do that. And please feel free to use chat box, because when I am presenting, I am not able to see whoever is speaking. So that chat box is there in the side. So you can write your questions, queries, discussion, anything. Feel free to write anything. Don't get shy. Everybody is new here. Everybody wants to learn something. Write it down. Any doubt, write it down. We'll discuss. Okay. So you will get your query answered. Or if there is some technical things which needs a broader discussion, then you have to sit on the discussion forum. So that more and more people can benefit from it. Avoid asking the current year assignment questions, because that won't be discussed. That is the guidelines of the NPTEL. Okay. So this is from my side for the course, and this is from my side. And let's hear you guys. So, any questions? Leave some formula for question answer. Venkata, have you gone through the slides? Okay. Have you gone through the slides? No. You are just jumping into the same directly. Don't jump. Uh, don't jump directly into the same. I think in lecture 2, we will, when you go through the slides, there are specific formulas there. Okay, you need to know how to apply. So don't jump directly. We will go to, or not go to that question. We will go to similar question in the previous round of experiments. I have not seen the 10th question, but I know that just have to talk about the side of studies and from those stories. So that is the easy one if we have gone through the slide. So please, I will suggest everyone to go through the lecture videos, go through the lecture slides. So don't worry, those questions are easy. Solve them very easy. Okay. Okay. So let's have an introduction of everyone here. So I will start with this first. So I may not be very good with pronunciation, but allegation D. So Allegation, can you hear me? Okay, so can Allegation, can you give a brief intro of one or two lines, like what is your background? Is it BSc, BTech, MSc, Masters, or anything? In which field you are working? Or anything? Just one or two lines. That's all. Allegation, are you speaking? Is muted. So he can unmute and ask it. No problem. He can unmute and speak and unmute someone else. Yeah, allegation you can unmute and speak. So if there is a problem, no problem. We'll come back again. So next is Jay. So Jay, can you tell something about yourself? Okay. Mhm. Okay. Okay, so yeah, there is a lot of scope in electrical engineering by integrating the solar energy, because electrical people generally or mostly work on this solar photovoltaic cells, but there are a lot of things like wind energy can also be integrated, hydro, solar. There are a lot of things, and even more progress is also seen in the solar thermal system. So we can have a conjuncture power plant with cool power plants and then solar thermal power plants. Okay, so yeah, there will be a lot of improvements in the field, and I think you have got a very good amount of work experience, like 20 years you said. Oh, that's very great. So I'm sure with this course we'll be able to get a good discussion with you also. So thank you, Jay. Okay, 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 okay. So yeah, sure, Jay. That's good to hear that you wanted to learn something new. That is what we do as an engineer. And then we got a message from Mr. Allegation. He's sorry for inconvenience. I don't have mic option. No problem, Allegation. I'm working as an assistant professor, Department of Mechanical Engineering, Excel Engineering College. Oh, that's great. You are a professor. So yeah, I think we'll get to learn a lot of things from you, sir. Okay, so that's a good thing to we have a working engineer with 20 years of experience. We have professor of Department of Mechanical Engineering also. Okay, so nice. That's nice. Next is Shine Hari. Sine Hari. So Shine Hari, can you introduce yourself? Okay. Hello, sir. I am Hari. I am pursuing BE Electrical and Electronics. Well, that's good to hear. Hari. So yeah, we'll get to uh, learn more with this course. Maybe if you go through the lecture slides, you will get to learn more of things. Okay. So it's okay. I don't have an option to mute myself. Why is there an option from my side? So, that's not from my side, na? Yeah, because Jay can unmute. Jay unmuted and spoke. So that's not a problem from my side. Hari, but no issues. Right. Okay. Vandana, uh, can we have some few Vandana is doing BTech electrical engineering second year student. Wow, great. That's good to hear. So I think all of us are seem to be engineers. So I was expecting a diverse background like from BSc also. So last time I was taking this solar energy course or something. So there were people from BSc background, MSc background, and they were very eager to learn about this renewable field. That's what I was really amazed to see that non-engineers or non uh, science background students are also very much. This is what it is. So we get to learn from everything. So from humanities student, arts students, so we can learn the policy, how we can draw policies. So I had a great discussion with two of the gentlemen last time. So they were in some, they had a background in policy or something, and we had a great discussion. How policy can be drawn for this renewable field and solar, why there is much push for solar, otherwise we can push for a wind also. So we draw a conclusion that no, India doesn't need a solar revolution. India needs a specific arrangement of specific renewables at depending on the location. Okay, so this is what we came to our conclusion. But yeah, there can be many things because India is a tropical country and lot of we had got a lot of sunlight. Okay, so and Arbaz is there. So Arbaz, can you introduce yourself with one or two lines? If you are not comfortable speaking, you can also write it here, like all other people. So I will suggest you guys to speak also. Like the problem with writing is it's okay, but when you speak, then you get confidence about asking question or something. Don't worry, I won't judge your English. Nobody is here to judge your English here. Okay. Sometimes I may not, I'm not very comfortable with maybe some other language, but I know many languages. So you can speak in your local language also. So I will try to learn. Many people will be able to understand maybe. Okay. Okay, Arbaj, uh, can you introduce yourself in one or two lines? It's, the problem with mic or something. Okay, next one is Suman. So Suman, can you, Arbaj is there? Okay, Arbaj. Yeah, go on. Okay, so Arbaj, what is your background? So are you from science background or engineering background? You are? Sorry, Arbaj, I could not hear you. Can you repeat? It's okay. I think got disconnected or something. So no problem. We have a diverse group. I wanted a diverse group of students here. So yeah, it's okay. No problem. Okay. So let's say you guys want to discuss this lectures, or you guys want to have a discussion on anything on any topic which you want on renewables or something. So what do you guys suggest? You can write in the chat box. So should I go to lectures and summarize the lectures? Like I have made some few slides on that. Then we can go through the uh, which questions also. So that is one part of this, or we can have a good discussion. So yeah, Arba. Mhm. So don't worry, Arbaz. We'll go through the equations. Those equations are not very difficult. Go through the lecture slides will be easy to solve them. But don't worry, we'll go through the previous year question and we'll solve those questions. I think so. Jay is saying that first brief about the course. So overall, this course is about mostly it's a renewable, like we will discuss. Uh, I think when you go to the first page, you will get to know about the different things like solar, wind, hydro, hydro, everything is there. So we'll discuss review of thermal, everything. Apart from that, we'll also discuss the techno-economic analysis or techno-economic assessment, like net present value, everything like inflation, index, etc. So that comes return, everything. So we also discussed in the so this is a very good course. Basically, the main focus will be on renewable because we are discussing the sustainable power generation. So I think before we start, let's have a discussion or let's have a summary of what is taught in the course, and in between we can have a discussion also. So let me start here. Okay, so this I discussed. Okay, so basically we have two terms in our course. We have written sustainable. The course is sustainable power generation system, but we need to differentiate between what constitute energy and what constitute a power. So this is a very basic definition which we learn in class 9 or 10th also, but but sometimes very basic things are actually skipped our minds. Very basic thing skips our mind. So we will again revisit the definition, like energy. What is energy? So in very simple terms, energy can be seen that capacity, that is the strength or the capacity to do any work. Okay, so if this is a calculator, and if you raise this calculator, so you need a capacity to do or raise from this side to this side. Okay, okay. So this to raise this height, we need energy. So what we are doing, we are firstly this was here, and then to raise this we moved it from here to here, so we increase the potential energy. Okay, and to raise this also we actually increase the speed, so kinetic energy was also there, and then after coming to this location, it came to rest this stage. Then the kinetic energy become zero, but it has all kinetic energy converted to potential energy. That's all. So this is what energy is, and we use this energy to generate power, or power in the power is not related with electricity. Electricity is also a form of power. Okay, power can be terms in terms of anything. Okay, and mechanical power is also a power. Okay, so what is power? Power is when you divide energy by time. So that is power, rate at which energy is converted from one form to another. So basically, when we are propelling a turbine, so that is mechanical energy. If we are burning a fuel, so we are that is chemical energy. When we are charging batteries, that is sorry, thermal energy, and when we are charging batteries, that is chemical energy. So by default, if you take any paper, this paper, let's say this paper, so this paper has some internal energy. So that internal energy is in the form of chemical energy stored in this paper because of its constituents CHNSO, carbon, hydrogen, nitrogen, oxygen and sulfur. So because of that there will be some energy associated with this paper. When you burn that chemical energy will be burned and it will be converted to thermal energy, that heat which you will feel. So that is chemical energy converted to thermal energy. Now, the rate at which this conversion is happening, chemical to thermal, is power. Okay. So how much energy is converted by a 100 watt incandescent bulb, light bulb? So 100 watt is basically 100 joule per second. So 100 joule per second is the now 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 100 watt. Okay. So let's say this incandescent bulb. Let's assume this incandescent bulb. So this incandescent bulb, and we rate it at 100 watt. Let's see how many of you can answer. So what is this 100 watt? Is it the amount of electricity, or is it the amount of light it generates, or is it the amount of thermal energy? Because there is a filament. Okay, that filament heats up and generates thermal energy. So is it the amount of thermal energy, that is heat, or light energy? Okay, HV, or electricity. What is this 100 watt? If you say 100 watt rating, anyone? Let's see if you can answer this. No answer? Okay, so let me then myself discuss it. Okay, so this 100 watt is basically the electrical energy which is supplied to the bulb. Okay, so that is the 100 watt, and it will convert some of the electrical energy to thermal energy in the form of heat. When you touch the bulb, incandescent bulb, it is hot, so that is thermal energy. Some of it will be emitted as wavelength, that is light which you see, so it will be converted to light. So that is light plus waste heat. So first law of thermodynamics is that if you have energy input EIN, and all the energy will be conserved. So E out in the form of light, and E wasted in the form of waste heat. This is what first law of thermodynamics says. So energy can neither be created nor be lost. If you are supplying 100 watt, then 100 watt will be there. 100 watt may be 80 watt in the form of light, and then 20 watt in the form of thermal energy. Okay. So this is what first law of thermodynamics says. So converting energy stored in fossil fuel, like let's say petrol or gasoline, whichever term you can use. So petrol has some chemical energy stored in it by virtue of its carbon and hydrogen bonds or something. Then we burn that petrol. So we burn the petrol, so thermal energy is generated, and that thermal energy or combustion pushes the shaft. So piston is pulled down. That piston is basically shaft work. So it is converted to mechanical energy, a high grade of energy. Okay, shaft work. Work is always a high grade. That shaft work rotates the, let's say, rotates the wheel. Okay, so that is in the form of kinetic energy. So I have taken a different example. You can take in form of power plant also. Coal turbine here, and then electricity. Okay, So you can take it in the form of this also. And basically, second law of thermodynamics says ki whatever energy output, net energy output we are getting, if we divide it by net energy input, so we can get an efficiency. So that is basically, that is not second law of thermodynamics. Second law of thermodynamics deals with the quality of energy. Like we'll discuss that also. So don't be confused. Basically, efficiency of coal thermal power plant is 35 to 40%. Second law of thermodynamics says, like, first law of thermodynamics, energy will be conserved. But second law of thermodynamics says ki no, every energy is not a usable form. Like we have to differentiate the type of energy. Like here we see we have chemical energy, mechanical energy, and electrical energy. Are all these energy same? So second law of thermodynamics says no. Energy has a quality like high grade energy, low grade energy. So heat is a form of low grade energy. Work electricity is a form of high grade energy. So we can convert electricity to thermal energy, but we cannot convert each of the thermal energy to electricity. So there is this entropy and all those things are actually came into pictures. Then Q by T is came into pictures, everything come into picture. So this is what second law of thermodynamics says. Okay. And question for you guys: what is third law of thermodynamics? Then is there a third law of thermodynamics? So we have first law of thermodynamics, second law of thermodynamics, and then we have third law of thermodynamics. That is third law is totally somewhat different from. So is there any third law of thermodynamics? What is zeroth law of thermodynamics? So learn about this zeroth law. Okay, this is up to you guys. So I leave it to you guys. Let's see if there are any questions or any discussions. You guys, here. Okay, so no discussion is here. No problem. Still have a lot of discussion. So this is what a traditional thermal power plant layout. So basically, if we say see a traditional thermal power plant, so I want you guys to first have a good uh, like visuals of this thermal power plant. So I will explain it later. I want you guys to first have a look at this thermal power plant. See whether is there anything unusual which you see or anything which you were actually like which you were actually observing earlier and then you can notice it out here. So please have a look. I think uh, those who have mechanical background can easily spot the things and much easier understand it. Maybe from electrical backgrounds also, but not so much in detail. But they must have been sure about this thing, this turbine, electrical generator. So they also must have known about these things also, not much in detail, but they must have a good idea. So please have a look at this traditional thermal power plant, guys. Okay, so this is traditional one. The new one, the current power plants are much more complex and not like this. Okay, so I will tell you guys where the current power plants how they differ actually. there anything which you guys can notice on this thermal power plant? Okay, so I did not notice any answers from you guys. So don't worry. I think electrical guys can have something, um, some parts or something which they can identify. So most of the time when we ask normal people about the power plant, so they observe this chimneys, these cooling towers, okay, and the chimneys. These are integral parts of the thermal power plants, these cooling towers. But nowadays, these cooling towers are actually sorted out and more advanced and complex cooling process are actually adopted. But these cooling towers are actually much more for a recirculating type of condensers. These are still this. So this is the boiler. Okay, boiler. What does boiler does? It produces steam. So it's like a regular normal boiler, but complex. Like we have a lot of tubes in that. Water circulates and it converts into steam because of high heat thermal energy here. So the flue gas from here goes to electrostatic precipitator where the particulates, the PM 2.5 or PM 10, like you observe a lot of Indian cities have this smog problem. So these are one of the major contributors of that smog problem. These particulates. Yeah. And there are some SOx and NOx uh, control devices also. So for SOx, there can be fluidi is desulfurization unit. Okay. For NOx control, there can be SNCR, certain or SCR, reduction. There are a lot of units there. This is for the flue gas. Now, now the steam cycle. Okay. This is flue gas cycle. This is steam cycle. So water is okay. Let's say we want some this goes through the boiler that got converts to steam, then it flows through the super fluids are there. Okay, so these are super fluids. Okay, so what atomizer does, it actually heats the incoming water with the residual flue gases. So I think atomizer participated here, residual flue gases. So after this superheating, it goes to the turbine. Okay, so this is where the mechanical will work. The turbine is how to work. And then turbine is connected with generator with shaft, and because of the rotation of the shaft, electrical energy is generated and that is circulated to this. So this is what it is: steam boiler. This is electrostatic precipitator, combustion turbine. Okay, 3, 4 is alternator or generator, and 5. Why it is alternator, not because alternator basically generates electricity with every cycle. Okay, transformer every half cycles. Transformer, okay, condenser. This condenser, and this is cooling tower. So most of the people talk them about power plants, so they will say very hyperbolic say cooling tower. So cooling tower is integral part of the thermal power plant. Now, power generation from renewable energy sources. So, we'll study all these one by one. So, there are several weeks, 12-week course. So, every week we'll discuss one of these. Okay. So, renewable power generation sources, solar PV and thermal, wind power, biomass power, hydropower, geothermal power, hydrogen energy, ocean power. So why we are actually studying these? So energy obtained from continuous or repeated currents of energy recurring in the natural environment is basically renewable energy. So this is what a definition by Tweedale and Weir. And because they are abundant, let's take an example of sunlight. Abundant, solar energy, abundant. You don't have any restrictions like fossil fuels that it will go zero in 50 years, 100 years. No, we'll have the solar energy. Until and unless there is a lot of greenhouse gases and the earth is covered with clouds and there will be no solar energy. So that is altogether a different scenario. But we'll have solar energy always abundant, sustainable. Sustainable because we can have a same level of energy usage, but for our children also they can also have the same level of energy usage. Okay, so that is sustainable. So resources are utilized in such a way that we don't hamper their the capacity of future generation to use the resources. So this is what a meaning of sustainability or sustainable is. So if there is 100 tons of coal for us, then 100 tons of coal should also be there for our future generation. It is not that 100 tons of coal is there, then you utilize all the coals and then for future generation there is only 10 tons of coal. That is not sustainable usage of a sustainable energy source. You have to use it in such a way that the capacity of future generation to use that resource doesn't hamper. That is sustainable development in real terms. Environmental friendly. When you burn a fossil fuel, what are the gases which generates? So what are the gases generates when you burn a fossil fuel? Can any one of you guys can answer? Let's say I will give you example of gases which generates. Let me write CO2. Now you guys write one gases. Everyone will write one gases which is generated from burning of fossil fuels. Right? CO, NOx, SOx, SCl. So SCl is not acid, it's a fume also. So it's kind of gas. So, okay. So there are a lot of gases which are generated from the where could uh, where could access this lecture after. So Vandana, this whole thing is getting recorded and I will upload the slides also. So this whole recording and the slides will be shared with you guys. Suman wrote a very good answer, CH4. So CH4 is generally not generated, Suman, at the power plant. Okay. CH4 is generated in anaerobic digestion, methanogenesis process. Methane is generated. Okay. But that's nice you are thinking on that line. Hari is writing SO2. Yeah, SO2, very good, very good. SO2 is SOx. Okay. Anyone else who want to write anything? Guys, there are a lot of so I will not teach you. I am not teaching you whatever is there in the lecture. I am actually discussing whatever extra which I can have in discussion. So this is what it is. SO2 is there, NO2 is there, N2O is there, NO is there, and we have particulates also. So particulates are not gases; they are very fine particles. You can say them PM 2.5 or something. Behave like gases, but they are actually solid particles. Okay, so next thing is that environment friendly is there, energy independence and security. I will not go into that. Everybody knows energy independence and security. What does it mean? So why energy security is important? So let's say we have this. Uh, let's say why we are talking about energy security. So let's say we open a world map. So I think all of you guys can see my screen. So you will see that most of the petroleum reserves, so most of we are very much dependent on the fossil fuel. So most of the fossil fuel are concentrated in this region. US also has some reserves. Some reserves are there here and there, but most Russia. But yeah, most of the resources are actually in the Middle East, and we have a good relation with Middle East. Okay, so let's say uh, there is a time when we don't have a good relation. After 50 years or so, maybe there is a lot of war because we can see a lot of war already going on in the Middle East, and then we take a side. Let's say we take a side of Israel, and then a lot of war will be there, and then these countries can straight away say that no, we will not will do any business with India. Okay, so you guys can actually understand what's going on here. Okay, so they will stop the supply of fossil fuel or cut the supply. Okay, let's say they are supplying 100 billion barrels, and they will say no, we will give only 10 billion barrels. We need much that for ourselves. So India doesn't have energy security because it is very much dependent on the import of fossil fuels. So, but if we convert our all systems on renewables, let's say solar energy, wind energy, we itself can have the plants here, the wind energy plants on the shore or solar energy here and there, and we can generate the energy, and we will not be dependent on these guys. Okay, for fossil fuels. So this is what energy independency and security term comes into play. Then we have economic opportunities and job creation because we are venturing into new field. Earlier this field was not there. So Jay was engineer, and he was saying that he has worked in this electrical field for 20 years. So earlier the electrical companies were mostly focusing on installation and then distribution, power generation, all those things. But now they are also venturing into this renewable field, and then they are hiring people who have experience in this field. So more and more people are going into this renewable field because this is a new field, so a lot of job creation is there. Okay, technological advancement and innovation because new technology has to be developed. Health and safety benefits, environment friendly, certainly health and safety benefits are there. I think there are lots of slides, and we should solve some questions. So this is what will make you guys more interactive with this interactive session. So let's say we'll discuss those slides later. Let's have a question first. So I will give you this question. In a power plant, two cycles are coupled in such a way that heat rejected by one cycle is absorbed by other. So let's say we have a Brayton cycle. Okay, okay, and then this heat rejected by Brayton cycle is actually used in, let's say, this Rankine cycle. So, so this is form. So I didn't draw it to the scale, but yeah, let's say they are coupled or somewhat. So let's say whatever heat is there goes to the boiler of Rankine cycle, then turbine, then there is pump, and then sorry, then is condenser and then pump. Okay, so this has efficiency of 0.45. This has efficiency of 0.39. Now, if we combine these two cycles, so what will be the total efficiency? Tell me, guys. Tell me the total efficiency. Calculate. So formula is there in the lecture slides. So you can use the formula. Otherwise, I will solve this question for you guys. And many people were asking that how this question can be solved. Basic, use the formula. That's all. Or if somebody wants to, let's assume 100 joule of energy is there, and then you can also calculate on those terms also, like how much energy will be there. No answers yet. Why? This is the formula 0.49. What was that? Let's do it, guys. 0.45. Formula is n1 plus n2. Like it's not n1, it's eta. Okay, and just for your convenience, plus 0.39 minus 0.45 into 0.39. So that comes out to be 0.45 plus 0.39 is 0.84 minus 0.45 into 0.39 is 0.18. That is 0.66. The correct answer is 0.66. Okay, so no problem. Don't worry about the questions. Just understand the question, how you can solve these questions. Calculate the thermal energy lost from an insulated tank with 1000 liters of olive oil for a temperature of 100 degrees Celsius. Boiling point is this. Olive oil density and specific heat is this. So let me tell you the formula also. mCp delta T. One temperature is here, another one is here. Okay, you have the olive oil, you have the density, you have the Cp value. Convert the liters into this using this 1000 liters is how much meter cube, then convert it into kg, mcp del t. Now apply and solve. I want the answer this time. No excuses. I want answers from each one of you. Yeah, I think one more thing. Del T is also given directly. Temperature drop is given. Del T. You don't need to evaluate del T also. Your CP del T, just you need to evaluate M and multiply all those. Let's see, any one of you have solved this? Okay, Suman has solved that question. Wow, that's great, Suman. Nice to see that you are actually trying to solve those questions. So, can you solve this one also? The MCP del T things? Let me wait for 1 or 2 minutes. So, if any one of you can solve it. Density of oil is mentioned in the problem. Olive oil density is 920 kg per meter cube. Hari has done it 920 into 1970 into 100. Wow, that's good actually. I think he has done it correctly. 1000 liter equal to 1 meter cube, so 920 kg. And correct. Okay. Now let's move to the another question. So this is theoretical question only, so no need to go into detail. So mind you guys, these questions are from previous run of the quiz. Okay, so you guys must have got an idea that how these can be done. So okay, so don't worry. These questions, if you are able to do this type of question, you will be able to do the current week assignment questions also. In dry steam power plant, the pressure and temperature of superheated steam lies in the range of. So first thing is that superheated steam is basically how much is the boiling point of steam. So steam boils at, sorry, boiling point of water, that is 100 degrees Celsius. So superheating is something above that. Okay, so if you draw a Rankine cycle, so this is the superheating zone, and this is the boiling point in the boiler. Okay, at 180 pressure. So this is somewhat above 100 degrees Celsius, and at, so these are pressure lines actually. Okay, so this is the correct answer. 4 to 8 MPa, 180 to 225 degrees Celsius. So this is purely theoretical basis. No need to calculate or something. Just you need to answer. The amount of electricity consumed by a 100-watt fan running for 5 hours. Very easy question. There are 2-3 electrical guys here. This is like a child question for you guys. So please do it. Amount of electricity consumed by you, which is the correct answer? I want you guys to solve it. Okay, Suman has done it. 0.5 kilowatt hour. So that's correct, Suman. Very good. So you just have to do it. First convert it to into kilowatt into 5.5 kilowatt hour. So this kilowatt hour is basically unit, which the Bijli, sorry, the electricity bill in your city or town comes in unit. Like you have consumed 100 units, so 1 kilowatt hour is equal to 1 unit in basic terms. In basic terms of understanding. So there are power factors and all those things also. So we are not taking into account. So 1 kilowatt hour is basically 1. The correct answer is answer B. The condition at which maximum temperature of flat plate collector attains is, so let's say there is some box, flat plate collector is a box. Okay, there is lot of solar energy on it. So when does this box or flat plate collector will attain the maximum temperature? So there are four options: useful, total heat loss is 0, re-radiation, reconvection is 0. So all those solutions are there. Okay, so many of you will jump directly and say that, sir, when there will be no heat loss, insulate all this, and then when there will be no heat loss, then the maximum temperature will be achieved. No. First thing is that what is the energy incidented on it? Q is into the area of collector, that is this area on which the solar energy is. Then with this we have some heat loss also, QL. Then if we subtract the heat loss from this term, we get QU, useful heat gain, that is being taken by the water which flows through the pipes here. Okay, water. So when this useful heat gain is 0, so you can equate these terms, Qs into A minus QL equal to 0. So this Qs into A will be equal to QL. Okay, and at that time, the all the heat that is supplied to the flat plate collector will go towards raising the temperature, because nothing is there to take out the useful heat gain. Useful heat gain is 0 here. Okay, so at that time this useful heat gain will be 0, and that will be used to raise this temperature, and at that time the maximum temperature of the flat plate collector will be attained. So the correct answer is answer A. Okay, let me see if any one of you has have the correct answer. Okay, Jay has actually calculated for the previous question. Oh, nice, Jay. So that's good. You guys are actually doing solving the numericals, and that is a good way to learn from the course. So I suggest you guys to do more and more these type of questions, so that you get acquainted with the assignments, and then you can easily solve these questions to get an idea about how these questions has to be approached. Now we have this in a combined cycle power plant, one gas turbine and one steam turbine combined to produce electricity. The efficiencies are this and this, the combined cycle efficiency. We have just solved this question. Question 1 was this. So I want you guys to solve this question. Combined cycle power plant. Okay. Solve it, guys. So let me see if any one of you has got any answer. 70% efficiency. Okay, great. Suman has done it 70% efficiency, and her calculation looks okay. So yeah, 70% efficiency not an option here, na? Okay, I think all the options are incorrect here. All the options are actually incorrect. So yeah, 40 plus 50, 90 minus 20. All the options are incorrect. So in that case, if these type of questions are there in the assignments, so don't worry. The marks for that assignment will not be counted towards the final marks. Okay. Now moving to the question number 7. The rated wind power of power plant is 5 megawatt. The annual capacity factor is 0.31. The efficiency is this. The annual electricity generation will be. Okay. Now let me see who will be able to do this annual electricity generation. Okay, Hari and Jay has calculated it to be 4881. Okay, Hari has calculated it to be 8760. That is also okay. 8760 24 into 3. 365. Suman has calculated it to be 4888. Similarly, Jay has calculated it to be same. Okay. So you guys are actually correct. So that is the correct answer. 4888. Yeah, 4888.1 is the option. The correct answer is answer B. Okay. So I think last two questions are remaining, 9 and then the big question, this 10 question. So let's discuss the 9, then move to the theory part, then come back to this biggie question. So I've taken these slides also to make you guys understand how this question will be solved. So I will let you guys to solve this question so that you guys get confidence about how I can solve this question. Don't worry, you will be able to solve this question. The question is not big or small. If you understand the question, you get the quantity, you clarify all the terms, you will be able to solve. That's all. That is the point of solving the question. So numerical questions are much easier to solve than theoretical. Theory, you have to put your brain, okay, this can be correct, this can also be correct. Numerical, easy. You just have to understand what the question is asking, put the thing there. That is correct. To generate power from the concentrating collectors, only beam radiation is used, only diffuse radiation is used, only beam and diffuse both are used, solar radiation is not used. So concentrating collector is term here, so solar radiation will be there. Okay, first thing is that. In both beam and diffuse. Now, what happens in concentrating collectors? Let's say this is the concentrating collector, this is parabolic disc collector, concentrated it on a focal point. Sunrise through our focal point. Okay, so this concentrates the sunlight to a focal point. So only the beam radiation, that is radiation which is falling at 90 degree to the surface in the form of a beam, are only concentrated. No diffuse radiation, not from this. Why? Because diffuse radiations are radiation coming from all other different angles, and they are, that's why they are diffuse. They are not being direct radiation. So if some radiation is coming from this side, so this will be scattered to there. Coming from this side, this will be scattered to here and there. So it won't be able to concentrate on that specific focal point. Okay, the focus. So that's why only beam radiation is used to generate power from concentrating collectors. Okay. Then the PE question. Okay, so before solving that PE question, let's take a break of let's say 5 minutes, because you guys solved a lot of questions and I'm sure you guys have a good understanding about how to approach these questions and solve it. And I want you guys to solve the assignment question and not come with the questions here like, sir, I am not able to do it. You will be able to do it. Don't worry. I'm here to help. Okay. So we'll move to this discuss some slides here. 6 slides, discussion type of slides. I want to discuss on this. I want just don't want to speak and speak on these type of slides. I want what you guys know about this, what you guys understand, and then we'll move to that final question, and then this session will be over. Okay. So before that, let's take a break of 5 minutes. So you guys, this is not a break. This is like you guys can go through the slides and then you can have, if anything you want to ask, please write it down here in the chat box so I can read and then we can have a discussion. Okay. Okay, guys, let's come back from the break. So I'm sure you guys must have got a good understanding. If there are any questions, please feel free to ask. So let us start solving question 10 because that's a very big question and it will require the effort, the discussion also. So let's start the question. So start. Now the first thing which you will do is to write all these terms. Okay. A flat plate collector is inclined at 30 degrees Celsius. This is the flat plate collector. It is inclined at 30 degrees Celsius to the horizontal. Okay. Facing south, ambient air temperature and mean plate temperature are, so TA, you know, 30 converted to Kelvin, sorry, 20 converted to Kelvin to 90. And the mean plate temperature, that is, let's say, is 75. Comes out to be 75 plus 273, which is that 348. The system is provided with 8, that is 8 thick bag insulation. Thickness of insulation, let's say TL equal to 0.08 meter. Always write it in SI units. 4 thick, like this. This is the collector. So this is insulation is 8 centimeter, and then side insulation is 4 centimeter. So TB, TS equal to 0.0. Thermal conductivity of the insulation K is given 0.035. The air space between the absorber plate and first glass cover. There is a absorber plate, then there is a glass cover. So air space is, let's say TG equal to, it's not TG, let's say TG equal to 0. First and second glass cover is also 5 centimeters. So glass cover TG1 and TG2. The emissivity of glass cover and plate is, so for plate it is 0.85, even, sorry, epsilon 1, epsilon p, covers Eg1 equal to Eg2 equal to 0.9. Size of the absorber plate, so you have L1 equal to L2. Okay, so absorber plate will be like this, which is fitted here. So that is 1.15 and 0.15. So now you have all the data. You have to determine the top loss coefficient. So coefficient from here, that is U value from here. Okay. So L1 equal to L2, you know, and the thickness of insulation, that is, it will go from here to here. Okay. So L1 equal to L2, you know, and L1 and L2, you know, L equal to, that is the distribution, that is 5 centimeter. Okay. Then we have epsilon P and epsilon G1, G2 is also given. And beta is also given, that is 30 degree. Then plate temperature and this ambient temperature is given. Is velocity of glass cover, the velocity of wind. Surprisingly, the velocity of wind is not given, so you can take it as velocity of wind equal to 3 meter per second. Okay, so this is necessary because wind will carry the energy from top glass cover now. Okay, so and this TB and TS is actually given, K is given. Okay, now top loss coefficient, you need to know the HW value. So for that you can use the correlation basically for HW value. So let's say this is the energy balance. I have discussed this also. Whatever coming the loss is equal to useful heat gain. For S you can use this equation, and for AP you know AP is basically L1 into L2. TPM is plate temperature and this is ambient temperature. Okay, average temperature of plate. So you know average temperature of plate here and ambient temperature here. Okay, and heat loss from the collector is sum of top, heat loss from top, the side, then bottom. So this is what it is: heat loss, top loss coefficient, and bottom loss coefficient. That is what it is need to be calculated. So UT, UB, and US is what you will be calculating overall loss coefficient. Okay. So for that, for top loss coefficient, Q2 upon AP, HPC1 TPM minus TC1 sigma TPM4 minus ECL4 1 minus EP upon EC. So that is convection radiation between absorber plate and first cover. Then there will first cover and second cover, two covers were there. One plate, then cover one, then cover two. You can see here. Plate, then cover one, and thickness is first glass cover thickness is 5 centimeter, and here is between first and second glass cover is 5 centimeter. So this one, and then this cover, and then for the surroundings. Second cover to surroundings. So basically, the beneath is plate, then we have one cover and then second cover. So for that, let's start calculating them. Then first thing which you need to do is to calculate there are many more formulas which I am not mentioning here. So first thing is HW value. So HW value you need to calculate. Okay, so HW value, how do you calculate the HW value? For HW value, you will use the correlation. So there are many correlation in the Adams correlation and other correlation. You will use 8.55 plus 2.56 into VW. Okay, so VW is 3. Put it here. You will get HW value as 16.23 watt per meter square cable. Okay, so you know the from the second glass cover to HW value. Okay, now you need to calculate the C value. Okay, so C value is basically you apply the formula 20, that is the formula mentioned in the slides. So let me open the slides here also. Apply the slides. Otherwise, it will be like where these formulas are actually coming. That will be very difficult for you to grab. Okay, so So this is the slide. So you can see from the slide. So this is the correlation developed by test et al. You can use the McAdams correlation also for HW. Okay. So we have used the test et al. Correlation 8.55 plus 2.56. Okay. Sky temperature basically T minus 6. Then you need to calculate the C factor. Okay. That is this the simplicity factor. Comes out to be is from the correlation also. You note down these correlation. 204.429 cos beta equal to 30 degree. You put the beta here 30, okay, to the power 0.252 upon L. What is L here? L is basically the thickness of glass cover, the space between that. 0.05 to the power 0.24. So C is calculated. Put the value where is calculated. This comes out to be 4.4.404.6 or something. Let's see. Okay, so we have calculated almost everything. Now we need to use the formulas. So now you have got this. Let me write. HW you have calculated and then C. HW is 16.3, C is 404.6. Now using another formula, you have to calculate basically the F. So I will let you, because F is basically shape factor. It's a factor basically used in, and there are lots of glass coverings above and above, then F factor has to be calculated. So to calculate F factor, you note down the formula. Okay, 9 upon HW, HW you know, minus 30 upon HW. Okay, TA, that is ambient temperature. Okay, how much was the ambient temperature? 293 K. Okay, TA upon 316.9. Okay, and then 1 plus 0.091 into the M is basically number of this glass covers. So there are two glass covers. So you will put, okay. So putting the values TA here 293 and 16.23 here. This comes out to be 0.4815. Okay. Now you have calculated. Now let me see. Basically these are simplified and then those values are actually calculated. Otherwise you can put the values here and then you can also calculate it from here also. Okay, you don't want to use those formulas, so otherwise you can use the formula given by P. Okay, now F is there. So another thing is that now there are many of these mirrors one after one, so you can use this formula for UT, that is M upon C on plate temperature T minus TA, that is plate minus ambient temperature, upon M value, that is M in, what is the M here? The two glass covers above the flat plate collector. So there are two glass covers, the value of M you have to take as 2, and the M value which you have calculated overall to the power 0.25. So you will learn all this correlation in the upcoming slides also. Okay. Upon 1 upon HW. HW value you have to put it from here, and 4 to the power minus 1 plus sigma. What is the value of sigma? Sigma is Stephen Boltzmann constant, 5.67 into 10 to the power minus 3. Okay. TPM square. So where does this come from? So this comes from basically, so whatever the energy provided by sun, then TPM minus epsilon 1 upon epsilon P plus 0.045 into M. M is basically here. Then 1 minus epsilon P and plus 2M plus F minus 1 upon epsilon C. Okay, so epsilon P you know, the glass cover epsilon P and epsilon C. Epsilon P is 0.90, epsilon G basically glass cover. Okay, and then minus M. This one. So put all those values, you will get UT as M equal to 2, C equal to 0.4815, TPM equal to plate temperature, okay, 348 Kelvin from here, TPM minus TM plus everything. So every value you know. So UT comes out to be 4.507. Solved. The correct answer is Rock loss coefficient. Then now if somebody says how much is the heat loss from the judge, how much is the heat loss? You know the UT. So UT into AP TPM minus that is the heat loss from the top. So heat loss from the top is very difficult to calculate actually. This is the heat loss. Then you have this heat loss from the top, and heat loss from the bottom is very easy. That is just UV equal to, okay, K value, K, what was the K here? This one 0.035. The side insulation thickness. Side insulation thickness is 8 centimeter 3 back insulation. UV is back insulation. Okay, so that comes out to be around 0.4375. The correct answer here is UV equal to 3. Okay. Now side loss coefficient. For side loss coefficient, you need to basically evaluate the total length. So L3, that is L basically 0.05 plus 0.05 plus 0.08. Okay. So total L equal to 0.18. Then use the formula US equal to L3 L1 plus L2 K upon L1 and 2 into delta S, that is thickness of side insulation. Thickness of side insulation in percent. Okay. So when you know 0.5 centimeter, 5 centimeter, is 0.8 and 0.18. And then you have L1, L1 is basically this 0.15. Okay. This battle control here 0.035 is the uh, thermal conductivity of insulation. So insulation wrapped cloud. Okay, so this is the update. So this is the okay, and then L1, L2 into delta L, that is thickness of insulation on the side. That is the OS as 0.1. Okay, so this is the yes, this is the formula. This formula is actually given in the slides. You can use it. And how this formula has actually come, you can see it from here itself. How this formula has actually evolved. So I think bottom okay. So with this, this session comes to an end. I solved the question. Just remember the formula and put the values and get the answer. Okay. So that's all from my side for this session. If there is anything which you want to ask, please feel free to ask. Okay. So go through the video to solve the questions. And if there are any problems, please feel free to put it in the discussion forum. And don't worry, those questions will be answered. If there anything which you want to ask, please ask here. Otherwise, we can conclude the live session here. Questions to ask? Thank you all for attending this live session. You can always find me here on the next Tuesday,